Yeah, thanks for the introduction, Heidi, and thanks everyone for coming today. So the title of my topic is quite long, but this is my essentially dissertation or thesis title, I guess it is now as a PhD student. And we're going to be talking about the development of the transonic and supersonic CFD modeling and design optimization techniques for application with space planes. So we'll break that down a little bit as the talk goes on. But essentially, I'm here today to talk about what it is that I do at Swansea, what I'm studying, what Swansea are contributing on the projects that I'm on, and a little bit about why that is important, or why I think it's important, and why it matters to all of us and why it affects us. So to start off with, I just wanted to give a bit of an overview of, as soon as my laptop doesn't crash, there we go. I just wanted to give a bit of an overview of the actual project, who's funding it and what it is we're doing, and also what it is that they do as well. So the company that are funding my research are called Reaction Engines, and we're working very closely with them, myself, my supervisors, Ben Evans and Sean Walton. And we're working on one of their kind of leading projects, which is called Skylon. And Skylon's a single stage to orbit spacecraft, which I'll talk a little bit more about in detail on the next couple of slides. But I would say that Reaction Engines aren't just an aerospace engineering company. I'd say they're much more of an applied technologies company. So over the last 30 years, they've been developing and researching a number of different products, one of which is a heat exchanger, which again, I'll talk about a little bit more in the next slide. And that's something that they've been now applying to a range of different industries. And they've got some really exciting opportunities going on in multiple fields. I think the one that interests me the most, other than aerospace, is Formula One. They keep that quite under wraps and quite tight to themselves, but it's really interesting to see the sort of work that they get up to. And over the last, I would say, 30 to 40 years, they've been developing something called Skylon. And essentially what Skylon's aiming to be is the world's first single stage to orbit aircraft, or spacecraft, sorry, I should say. And one of the big challenges that we face in the aerospace industry is a balance between payload, fuel, and getting it all up into space, and the weight of spacecraft. And if we want to increase the amount of payload that's going up into space, or if we want to get there in one stage, so that's without boosters breaking off, we need more fuel. But in doing that, we end up with more weight on the spacecraft, which requires more fuel to get that weight into space. And we end up caught in a loop where we're essentially trying to increase the fuel and weight, and we can't really get that balance right. And so what Reaction Engines have been trying to do is use the air that's sort of in atmosphere as a source of that fuel. So rather than having the extra weight on board, they can just get that fuel directly from the air, surrounding air. And one of the big challenges that they've been working on over the last 30 years is essentially taking that air as it's coming in, cooling it down from really, really hot temperatures, and making it sort of liquid and usable within the engines. And that's on the diagram on the left-hand side, we can see there's a pre-cooler stage towards the front of the engine. And that's essentially what they've been working on, which maybe doesn't sound like a lot, but it really is, I would say, a technological innovation that is absolutely second to none. The work they've done there is incredible. However, the design of this actual spacecraft itself hasn't changed much over the last 30 to 40 years. And that's where we kind of come in, and that's where our project's working on now, is we're looking at optimizing and improving that design with them. Now that they have all of the technology in place to make this spacecraft viable, they're looking to sort of try and bring that into creation and improve the existing design. My laptop doesn't freeze again. Yeah, there we go. And I think the big question really to ask now is why us? Why Swansea? Reaction Engines are based in Oxfordshire. It's not particularly close to us. We haven't worked on projects with them necessarily before, or not at least major projects. So what is it about Swansea that attracted them to us? And to answer that question, we really need to look back to a couple of large projects that we've been working on over the last 30 to 40 years, starting with Thrust SSC, which I think SSC stands for, I don't actually know what that stands for. I should probably know that one. Don't know if Sean maybe knows.
Supersonic car.
Oh, that's the one. Yeah, that makes sense. So Thrust SSC and also the next project, Bloodhound LSR, are both land speed record attempts that Swansea have been working on closely with other engineers in industry. The contribution that we had to both of those projects was on the CFD, or computational fluid dynamics side of things. So we essentially analyzed the airflow, tried to validate and test the designs. And in the case of Bloodhound, we also worked on development and improving that design. And the codes and the software that we developed for that have then since been tried, tested, and proven to be extremely accurate in something called the transonic regime. So when I say the transonic regime, what I'm referring to is around about the speed of sound, roughly about Mach 1. The airflow over any kind of vehicle, so in this case a car, or in the case of my project, a spaceplane, the airflow is very, very complex and very, very turbulent, and it's very, very hard to simulate. However, obviously our software has been tried and it's been tested in this region. Both of these projects were, or both Thrust SSC and Bloodhound were quick enough to approach the speed of sound. I think, I'm not sure if Bloodhound actually broke the speed of sound yet. I think that's the next milestone. I'm not actually quite sure. I should probably check that one with Ben. But certainly the Skylon spaceplane, when it's developed, will be traveling through the speed of sound quite quickly and very early on in its flight path. In fact, it's actually going to be going up to about Mach 25, which is 25 times the speed of sound, so fairly fast. And I think that's what really attracted reaction engines to Swansea. It's this proven capability that we have. However, it's not just this analysis. With Bloodhound, we also spent a lot of work developing and improving the design. And this was something that kind of happened over the course of a few years, where every few months there would be a new design iteration where a team of engineers would sit down, work on the design, they would optimize and improve it based on the previous iteration. And that whole process, I would say, per configuration took 2 or 3 months all in all. And obviously, as we can see on this diagram on the right-hand side of the screen, there was I don't think this necessarily paints the full picture of the entire development cycle, but even just looking at this, there's about 12 configurations. If we assume 2 to 3 months for each one, that's 2 or 3 years worth of development to go from the initial baseline design to an improved design. And in industry these days, I think 3 years is a big deal. A lot can change in that time. Other projects and other companies can come along and achieve exactly what you were trying to do over this time. And so it's really, really critical that we don't just focus on the actual design of vehicles these days, but also the design process and how quickly we're innovating those designs. And that's kind of where my PhD comes in. So the problem that we have is that this optimization stage takes a long time. And what we're looking at right now is how we can improve that. Obviously, a side benefit of that is that we will also be improving the design of Skylon. But the main focus really is on how we're going about improving it. So to give a kind of overview of exactly what we're doing a little bit differently, if we look at the standard process, so this is usually what happens within the development cycle. We start with an initial design. It can then sometimes take up to a few weeks to create a computer-aided design definition. So that's a continuous model, basically a computer model of whatever our design we want it to be. We then generate a discrete mesh for this. So this is just a surface and volume mesh made up of lots of different nodes and elements. That again can take days or weeks. If there are problems with that stage, which there very frequently are, and this is something that I've seen firsthand in my project, and pretty much anyone that's worked with going from CAD to mesh generation has encountered as well, this can even take up to months if there are major problems with that. We then take that mesh and we run a CFD analysis on it. That can take a few hours, can sometimes take days, very, very computationally expensive, but obviously a critical part of the state of the development cycle. Once the CFD analysis has been run, we then get a picture of what the airflow over the aircraft looks like. And we can go through this manual redesign process where we sit down with a group of engineers or a team of experts and look at where we think we can improve the design. That can, well, I mean, it can take as much as one meeting or maybe take a few meetings. And then we essentially just have to go back to the start where we change that original CAD definition, change the design, and go through the whole process again. The difference that we're trying to do in our project is have that talk a little bit earlier on, and then try and reduce the amount of time that we're spending on all of this mesh generation and converting the continuous CAD into the discrete mesh. So it starts off roughly the same. We have an initial design, then spend a few days, possibly even weeks, defining that in a computer model. What we then have done is we've sat down as a team of engineers and parameterized our problem. So we started with an initial baseline for Skylon, and we had to think about what areas we thought might provide some kind of benefit if we were to change. So for example, making the fuselage a little bit longer, or there's something called basically fuselage pinching, where we shrink the central section of the fuselage a little bit to try and reduce the drag. We could have discussed other things like changing the size of the wing, but we've largely been focusing on the fuselage for now. And essentially we came up with a list of parameters and said, okay, we want to change some of these within certain bounds and see what effect that has on the design. That whole process was conducted over a couple of meetings. Obviously, it took a little bit longer than it would normally because we were sort of defining and creating the process as well as deciding the parameterization, but that in theory could be done over the course of just one meeting. We then created the mesh as before, which took a little bit of time. However, rather than just creating that one mesh, we then used mesh morphing techniques using some software that we've developed in-house to essentially implement a range of 60 different random configurations based on the parameterization that we made. This led to then 60 different analyses that were performed. Again, a few hours or I think it was a couple of days running those CFD simulations. And we then had a picture of how all of our different parameters had improved the design. And then in the space of minutes or hours, we were able to analyze that data set, try and find an improved design and redesign the initial configuration, all while staying in the discrete mesh domain. I think what's critical here is that we've been staying largely in the mesh domain rather than going back to the continuous CAD definition. The benefit there is that we save on this days or weeks worth of trying to go from CAD to a mesh. And that's actually something that's been massively beneficial for us during this whole process. Oh, and my laptop's crashed again. It's not very good at skipping slides. There we go. So what's the actual progress that we've made on this so far? We've got a couple of images of the results or the kind of the airflow that we've performed so far. So along the top of the slide here, we've got the original design. And what we're looking at on the left-hand side is the actual mesh for the fuselage. We can see it's a very, very nice mesh that's created by some in-house software by, I think it was partly written by Sean Walton and lots of others as well within the engineering and computer science departments. But we've got a very nice looking surface mesh, and we can see this like central part of the fuselage. So this is what we're looking at is basically the middle of the aircraft, around about where the wings and the engine are. And just to the right of that, we've got the airflow simulated at Mach 1.2, so slightly quicker than the speed of sound. And we can see there's a lot of shocks, and it's a very complex shock pattern that's occurring throughout, well, across the whole fuselage. And some of the parameters that we've then changed led to the design on the bottom. So we can see the topology for the mesh here is identical. However, some of the nodes have quite clearly been squeezed and compressed. So in the central section, we can see they're quite tightly packed, where they've then been stretched to the left and the right of that. And if you look closely at the right-hand diagram, hopefully you should be able to see that the nose of the fuselage has also been drooped down a little bit, kind of like Concorde, where it had a bit of a drooped nose, only ours is a little bit more of a subtle droop. They're just some of the small changes that were made. And this whole process of converting the original mesh to this new mesh took, I think it took about 5 minutes for our software to implement. Obviously, it took a little bit longer for us to work out what changes need to be made. But once we decided what changes needed to be made, they were done within a few minutes, and we were running a CFD solver to try and improve this design. If we were still sticking with our old process where we were going back to the CAD definition, then this would have been a little bit trickier, and it would probably have taken us up to a few weeks. We wouldn't have been able to see results for quite a while. All in all, this led to about a 1.4% reduction in the drag. So the whole kind of reason or the whole kind of objective function behind our study is to try and reduce the drag over the spacecraft during the transonic regime. And a 1.4% reduction is quite significant within the aerospace industry. That's margins like that don't tend to come easily. So we're quite, I think, fair to say we're very pleased with the progress we've made so far, but obviously have a very long way still to go. the next kind of steps for us are going to be looking at working closely with a few members of the computer science department, actually, on implementing some sort of evolutionary algorithms to better explore the design space. So at the moment, we've just pretty much started with a Latin hypercube sample, analyzed essentially a bunch of random designs, and then tried to see where we think the minimum or the optimal results are within that set. But we're hoping to use some evolutionary algorithms to explore it a little bit more intelligently. But I think the big question is, why does this all matter? Sort of why does any of this matter to all of us? Why do we care? And I think in terms of the design process, I think this is something that companies really, really need to be thinking about these days. As I already mentioned, if a design process or an optimization process is taking years, then that gives a very large window for other companies to come along and do the same thing but quicker. Industry is very, very competitive these days, and we're always looking to try and have quicker design cycles. It also allows us to increase the amount of cross-discipline design that's going on. So if we're able to analyze designs quite quickly, we can sit down as a group, have a chat about what we think needs to be done, and then rather than having to wait months before coming back and sitting again as a group, we can look at those designs. I think in the long run, we're hoping to do it, almost real time. But obviously, the way that the computational, essentially the simulations we run are very computationally expensive, and so that still takes quite a while. But if it's able to take days instead of months, then that allows us to just sit down as a group a lot more frequently. We're also hoping that by using evolutionary algorithms, we start to see some more innovative designs. So things that we as engineers maybe wouldn't think of initially, which is always going to be, which is always interesting to see some of the designs that these algorithms pluck out. In terms of space access, so like the actual project itself with Skylon, I think it's personally, I think is absolutely critical. I've personally been a massive fan of reaction engines for longer than I care to admit. I was a huge fan of them before I came across this PhD opportunity. And so obviously when I saw it, it was perfect for me. But I think space access is something that as the human race, we need to be focusing on. It really is the next frontier for us. I think it's fair to say that all of us regularly use things that rely on satellite applications. So GPS, cell phone service, everything. It's almost an integral part of our daily life. But also the wider scientific community. I think having access to zero gravity environments for testing is something that's becoming increasingly important, and bringing the cost of that down is always beneficial. And that's something that Skylon and the work that reaction engines are doing is trying to offer. And I think there's a lot of indirect economic benefits as well from cheaper space access, sort of things we wouldn't necessarily think of. So I know certainly in the long run, manufacturing in zero gravity environments is something that's will provide a lot of benefit to a lot of different sectors and a lot of different industries, but they're not necessarily the sorts of things we might necessarily think of initially. I know asteroid mining as well actually is something that the UK are, I would say, leading the field on, but it's still quite a slow and emerging field. Certainly one day that'll be quite an interesting one. And that's something that reaction engines are really, any kind of space access is essentially what reaction engines are quite keen to get involved in. As I mentioned before, though, I would say they are primarily an applied technology business. So they are looking at using all of the technology that they've developed and applying it to other sectors, which again, I think is quite exciting for our project, because that kind of gives us the possibility of working on other things in the future as well. And if I remember correctly, that is, I think, yeah, there we go. That's the end of the talk. If there are any questions, I'm happy to take them now, or if people want to email me, feel free. We can have a little chat about anything that's maybe taken an interest to you. Otherwise, thank you all for coming, and I will pass back over to Heidi.